Okay, in the third part of the lecture, we're going to talk about axisymmetric stresses and displacements. Okay, in the previous section, we saw that for axisymmetric case, we end up with this simpler relation for compatibility equation. In this part, we're going to see how to further simplify it through analytical integration. As you can see, we have 4 times differentiation with respect to r. So we have to integrate it in 4 steps with respect to r. Let's start by the first integral. We're gonna end up with r. Basically, we're gonna keep whatever is inside here, and you're gonna have r1 divided by r phi comma r comma r here, and for the other side it's 0, so the integration with respect to r gives us a constant c1. I name it. Okay, now I'm gonna again keep everything here as it is, and just bring r to the other side and integrate whatever we end up having here with respect to r. So basically we're gonna have 1 divided by r phi comma r equal to the integral of c1 divided by r dr. Okay, so it's gonna be 1 divided by r phi comma r equal to 1 divided by r, the integration with respect to r is basically ln of r, and just don't forget that we get another constant here. This time again, whatever is inside the brackets remain the same, but we're gonna just take 1 divided by r to the other side and integrate from the other side. So it's gonna be like r phi comma r equal to the integral of c1 r ln of r plus c2 r with respect to r. Okay, calculating that integral gives us r phi comma r equal to c1 r ln of it gives us c1. So r ln of r is basically r squared divided by 2 ln of r minus r2 divided by 4 plus, and for c2 r, the integral becomes c2 r squared divided by 2 plus a new constant c3. Again, we're going to just bring r to the other side and integrate with respect to r to get the phi itself. Just pay attention that we end up with phi comma r equal to C1 divided by 2 r ln of r minus C1 divided by 4 r plus C2 divided by 2 r plus C3 divided by r. Okay, for simplicity, I'm gonna name this one C1 prime, because that's basically C1 divided by 2 is a constant. So I don't want to repeat C1 divided by 2 everywhere, so I name it C1 prime. And also, I'm gonna name minus C1 divided by 4 and C2 divided by 2 C2 prime, and I just keep C3. So it is equivalent to having C1 prime r ln of r plus C2 prime r plus C3 divided by r. Okay, we ended up with phi comma r equal to C1 prime r ln of r plus C2 prime r plus C3 divided by r. So basically integrating the right side with respect to r, it gives us phi equal to C1 prime r squared divided by 2 ln of r by integrating the term r minus r2 divided by 4 by integrating the term ln of r plus c prime 2 r squared divided by 2 plus c3 prime ln of r and c4, which is a new constant due to the new integral. Again, the same as before, it is like c1 prime divided by 2 r2 ln of r minus c1 prime divided by 4 r to the power of 2 plus c prime 2 divided by 2r to the power of 2 plus c3 prime ln of r plus c4. Again, minus c1 prime divided by 4 and c2 prime divided by 4. I can just name it c2, a constant. For c1 prime divided by 2, I can just name it a constant like c1, doesn't matter really. And I keep c3 prime, just I don't like prime, so I just rename it to c3 and I keep c4. As a result, our compatibility equation, the integration resulted in an analytical solution for phi. So it basically says for the compatibility equation to be satisfied in axisymmetric case, the area stress function should have this format with C1, C2, C3, and C4 constants, and being a function of r with r square ln of r term, r square term, and ln of r term. Okay, so basically axisymmetry property simplify the equations a lot, and enabled us to analytically integrate the compatibility equation to get the form required for area stress function. So we don't need to guess that anymore. Okay, now having the area stress function, we already know the relation between the stress tensor in cylindrical coordinates with area stress function. So it's a matter of just simply substitution. We're gonna get 1 divided by r c1, the derivative of phi with respect to r, it gives us c1 2r ln of r plus c1 r square 1 divided by r, that is resulted from the derivative of ln of r, plus 2c2 r plus c3 divided by r, c4 vanishes. I'm going to simplify it further. Don't worry, it's just a matter of collecting similar terms. But for phi comma rr, I basically differentiate the term here once again with respect to r, and it results in 2c1 ln of r plus 2c1 r divided by r plus c1 plus 2c2 minus c3 1 divided by r to the power of 2. Okay, I'm going to simplify that as well. It remains 0, and for sigma zz, we just add the solution from for sigma rr and sigma theta theta, and the result is, I'm going to keep it for after seeing the simplified solution for sigma rr and sigma theta theta. Okay, so basically sigma rr is reduced to this form. We just collected similar terms. Sigma theta theta is reduced to this form. And sigma zz is just a matter of nu multiplied by sigma rr plus sigma theta theta, which is equal to 4 times nu multiplied by 4 times c1, or basically c1 multiplied by 4 plus 4 ln of r. Well, there's no need for that. You simply see that substituting 1 and 2 there, we end up with 4 times nu multiplied by c2 plus c1 plus ln of r. Okay, it cannot get any easier. So it's almost time to solve an example and see how to work with it. In summary, successive integration of compatibility equation gave us a proper form for a stress function phi. Then we substituted the stress function in the equations, the differential equations we had for stresses in cylindrical coordinates, and we found the stress elements as a function of the constants in the stress function. And just as a hint, know that for the displacement, we can have displacement along the radius UR and displacement along the tangent direction U theta from these two relations. Note that as a result of integration from a strain to displacement, we gonna have a few more constants except C1, C2, C3, and C4. You see C1, C2, C3, and C4 here, but you see that we have C5 and we have C6, which are resulted from integration to find displacement from a strain. But don't worry about the mathematical details. It's not a mathematical class, but we're gonna need them to solve a few practical examples. Okay, before moving to practical examples, let's talk about Laplace's law. It's basically describes a very simple engineering approach to find circumferential stress in thin-walled pressurized cylinders. So assume we have a cylinder. It has inner radius, outer radius, a length, and it's under internal and external pressure. Let's cut it with this frictionless cutting plane. We end up with half a cylinder. As you can see, if there's a pressure inside, or basically a difference between the inner pressure and outer pressure, we can assume that all the pressure, the force resulted from the pressure inside, is cancelled by forces acting on our frictionless cutting plane. And since those forces are in the tangential directions, these are basically sigma theta theta, or basically there are circumferential stresses in that cylinder. And then pay attention, we can assume this frictionless cutting plane with any polar angle with respect to the axis. So we may end up with having the same plane here, or having the same plane here, or here. So basically we can assume that sigma theta theta, or circumferential stress, is going to be the same everywhere. Okay, let's work that out. Just pay attention that the force resulted from the internal pressure has an angle called theta with the cut plane. Okay, so as a result, we can say if this is the pressure direction at angle theta, it has only an element PV that acts basically parallel to sigma theta theta, our circumferential stress. So to calculate sigma theta theta based on P, we have to just think about PV, the projection of the pressure P with respect to theta. Okay, the pressure, the force caused by sigma theta theta is easily equal to 2 times sigma theta theta HL. So HL is the area, and 2 because we have 2 of these areas. On the 2 sides of the cylinder. And for the force resulted from the internal pressure, and let me tell you, the P can be actually the difference between internal and external pressure. But we just keep using P because it's simpler. We have to integrate from 0 to pi over theta, and we have to just sum PV and then multiply it by dA, the area of an element here. Okay, we already know that PV is the projection of P, so basically PV is P sine of theta, and also we know we can say that dA is A, the radius, multiplied by d theta, a small increase in the angle, multiplied by L, the length. So basically it is equal to P A L, the integral of sine of theta d theta over 0 to P. Okay, we can just cancel L, and the integral becomes PA minus cosine of theta for the range of 0 and P, and it is basically simply 2PA. Okay, so we can say that sigma theta theta is PA divided by H, because, well, these 2 and 2 here cancel each other. And that's a very simple way of finding circumferential stress everywhere in a thin-walled pressurized cylinder. The applications are, as we've seen before, vascular aneurysm. The aneurysm may take a cylindrical shape, so what we've learned so far can be used to find the circumferential stress on the blood vessel, and that's the cause of rupture in the blood vessel. An interesting point might be that the radius of curvature of these aneurysms results in a higher circumferential stress and more dangerous cases rather than the size. So you see, for example, here we have a larger aneurysm, but since the radius of curvature is larger, we get a smaller circumferential stress compared to here, where the aneurysm itself is smaller, but it has a smaller radius of curvature as well. So the size of the aneurysm doesn't matter. The radius of curvature is the thing that matters and results in higher circumferential stress, as you can see here, and makes the aneurysm more dangerous. Okay, we're going to see the difference between using Laplace's law to find circumferential stress with our more precise way of calculating that based on area stress function in an example in the next section.